So we're going to revisit this idea of a difference equation, and we're going to use a similar example that we did last time when we were talking about difference equations. Remember, a difference equation is, say, the next vector in a sequence is equal to a matrix times the previous vector, and we also showed that that was the same thing as let me write it this way. X to the nth vector in the sequence is actually a to the nth power times the initial vector. Okay. So this problem says in a certain region, about 6% of the city's population moves to the surrounding suburbs each year, and about 4% of the suburban population moves into the city. In 2015, there were 10 million residents in the city and 800,000 in the suburbs. Set up a difference equation that describes a situation where X naught is the initial population in 2015, then estimate the populations in the city and in the suburbs 2 years later in 2017. What is the long-term behavior of the populations? So it's got two parts. I actually got a lot of parts, but there's two questions in the problem. Estimate the populations in the city, and what is the long-term behavior of the populations? All right, so let's set up the matrix A. All right, so let's do city and suburbs, and city and suburbs. So we're going to go from here to here, right? So in the city, 6% go to the suburbs. So we'll put the 0.06 here. That means 94% stay in the city. And for the suburbs, 4% are moving to the city. And that means that 96% are going to the suburbs. Our initial vector is our initial population. We've got 10 million and 800,000. All right. So, one way we did this is I would say, let's make matrix A so I'm just going to use my calculator here. What about vector X? We'll call that B. And if we multiply A times B, we get the population in each after 1 year. So A times X naught will be X of 1. So this will be 2016. We're rounding here. Okay. And then if we wanted to find the population in 2017, we would need to multiply x1 by a, which is the same as multiplying a twice, or a squared times the initial vector. So let's say a squared times b, and that gives us the population after 2 years. So again, these are rounded. Sorry, my dog's going crazy. Okay, so how are we going to do this long-term behavior? So this is where we're going to introduce eigenvalues and eigenvectors. So let's take this matrix A and let's find the eigenvalues and eigenvectors. So I need to find the determinant of A minus lambda I. So I'm just going to subtract lambda from the main diagonal. And take the determinant. So I multiply this diagonal. I'm going to subtract this diagonal. I'm just going to use my handheld calculator to do a few of these multiplications. This looks very messy because of all the decimals, but we'll see how it works out. Don't despair. So I get lambda squared, after I simplify, I get lambda squared minus 1.9 lambda plus 0.9. Right, if I take this minus this, you just get 0.9, and I combine these together, I get 1.9. All right, so we set this equal to 0. We could try to factor it. Let's just use quadratic formula. So lambda equals negative b plus or minus square root of b squared minus 4 times a times c divided by 2 times a. Just got to do all of our calculations correctly here. And the square root of 0.01, that should be 0.1. So this did factor. I just didn't give myself time to figure it out. All right, so we got two options here. We got 1.9 plus 0.1 over 2. And we've got 1.9 minus 0.1 over 2. So this would be 2 over 2, so that's equal to 1. And this is 1.8 over 2, which is 0.9. So you get 1 and 0.9. So that was probably easy. We just didn't, that was easy to factor. We just didn't give ourselves a chance there. So I get lambda 1 equals 1, lambda 2 equals 0.9. All right, now we're going to find eigenvectors. So for lambda equals 1, we need to solve a minus lambda I, and I should replace lambda with 1. So a minus I, x equals 0. So I just need to subtract 1 from the main diagonal and augment with 0. And we'll solve for the eigenvector. So let's see. 0.94, 0.96. So 0.94 minus 1 would be negative 0.06. 0.96 minus 1 would be negative 0.04. And we can see that if I add these together, I'll get 0 in a row, right? If I add the first row to the second, well, let's divide this row by negative 0.06. So I get 1. This will be negative, and it'll be 0.04 over 0.06. So that's 4 over 6, which is 2/3. You get negative 2/3. All right, so let's say this is x1, x2. x2 is free, so x1 is 2/3 x2, and x2 is whatever we want to make it. We're going to actually choose an eigenvector here, so let's let x2 be 3 so that it cancel out the fraction. So let's say first eigenvector is 2 and 3. Right, we're going to do this again for 0.9. So I need to solve a minus 0.9 times I. I forgot the times I. I'm trying to write too fast. Times x equals 0. So I need to subtract 0.9 from the main diagonal and augment with 0. So this was 0.94. If I subtract 0.9, I'll get 0.04. This was 0.96. If I subtract 0.9, I'll get 0.06. If I divide this row by 0.04, I'll get 1, 1. If I divide this row by 0.06, I get 1, 1. Let's need to subtract the rows. Whoops. Subtract the rows, and I will get my Rref form. And this is x1 and x2. x2 is free, so x1 equals negative x2. So x2 is whatever we want to make it. Let's just make it 1. So this would be negative 1. So our second eigenvector would be negative 1, 1. Okay. So here's where we're going to get cute. All right. So these two eigenvectors are in R2. They are linearly independent. That means they span R2. That means we can generate any vector we want by taking a linear combination of v1 and v2. So what I'm going to do is take this initial vector, this 10,800,000, I want to write it as a linear combination of v1 and v2. So let's write that down. So I want to say, let's write x of 0 as a linear combination of v1 and v2. So v1 was 2, 3. v2 is negative 1, 1. So I just need to solve this for the c's, which means I need to solve this system. And I'm solving for C1 and C2. Those are my constant weights, my variables. All right, so let's make a new matrix here. 2, negative 1, 10,000,031,800,000. I'm going to row reduce that, and I get these two solutions. So I get C1 is 2,160,000. C2 is negative 5,680,000. I think that's a 6. Let me rewrite that. Okay. So that means that x sub 0 is C1 times V1 plus C2, which is negative, times V2. Okay, so this is constant times this vector. Let's just leave it like this. Okay, all right, so when I'm multiplying by A, and I multiply by A times our new vector. So I'm going to write it in shorthand here, so I don't have to write all those things out. When I multiply this matrix times its eigenvector, right, this distributes, and I can factor out the constants. Because these are eigenvectors for this matrix, when I multiply by A, it's the same thing as just multiplying lambda times the vector. And same thing here. This is lambda 2 times V2. So when I multiply by A, this A times x naught, it's the same thing as C1 lambda 1 V1 plus C2 lambda 2 V2. And we get the same thing. So what happens if I multiply by a second A? Oops. So if I multiply these by A again, I multiply V1 and V2 by A. Remember, you factor these constants out. The lambdas are constants as well. They're scalars. Then I'm just going to get another lambda times V. So this would be lambda 1 squared V1, lambda 2 squared V2. And in general, A to the nth power will be C1 lambda 1 to the nth power V1 plus C2 lambda 2 to the nth power V2. So we used, before we used eigenvalues to diagonalize a matrix so we can take this high power. But if we use the eigenvectors too, all we have to do is raise these constants to these powers. All right. So that means this is x of n, right? So if I want to know what happens when n goes to infinity, what I'm saying is what's going to happen to this. C1 was, what was it? 2,160,000 times lambda 1, which was 1 to the n, times V1 plus C2, it was negative 5,680,000 times lambda 2 to the nth power V2. So what's going to happen to this? What's going to happen to this thing as n goes to infinity? Well, if a number is less than 1 or between 0 and 1, like this guy is, and n goes to infinity, this is going to go to 0. So this whole thing is going to drop out. So as n goes to infinity, 1 to the n is just going to be 1. So this guy is going to balance out, right? It's going to reach an equilibrium where our populations are going to equal this. So let's see what this is. I'm going to multiply the 2 million times 2. And I'm going to multiply this by 3. So this would say, we would say our populations stabilize at, we'll say the city at 4,320,000 people, and the suburbs at 6,480,000. And getting this difference equation into this form, into this eigenvalue eigenvector form, helps us determine, this. Now let's say that instead of 1, what if this was 1.2? Well, then if we raise it to the nth power and we let n go to infinity, this is going to blow up to infinity. And that would mean our populations would just blow up. There would be no stabilization. If this was 0.8 instead of 1, like the 0.9, this would go to 0 and our populations would go to 0. Eventually, there would be no one in the city or suburb. So I don't think either one of those makes sense. But what we actually got makes sense is that if this trend continues with the 6% and 4% migration, that eventually you're going to get to a point where when you trade those off, you're going to get the same populations in both places. So this is used in a lot of different applications. So this idea of the difference equation and using the eigenvalues and eigenvectors to analyze what's going to happen in the future is very useful.